Broadcast is now starting. All attendees are in listen-only mode.
Okay, it's 2 o'clock, so we're going to go ahead and get started. Welcome everyone to the weeks 3 to 4 S2S webinar series. My name is Karen Keith from the Office of Science and Technology Integration. Before we get started, just going to go over some background information. If you have any questions for our presenters, please put them in our Google discussion document. The link is in the chat. It should have been there when you first joined, but I will also put it in there a couple more times throughout the presentation. So please type anything for the presenters there, and we will go over the questions when we have time or even after the webinar. And we have a VLab website. If you just Google week 3 to 4 S2S webinar series, that should be the first thing that pops up. Here you can find the links to register for each month's webinar. Also, if you would like to receive emails from us, which will give the registration information, please subscribe here. And if you are interested in giving a talk to our monthly webinar, please fill out our form and we can get you set up. We do have some open positions starting in June for the summer. So if you have a talk, a 15 to 25-minute talk you'd like to give, please fill your information there and we will contact you and set up a time that works. Again, we have slots available starting this summer in June. And if you missed any of our previous webinars, we have them all listed on our website. And if you click on one of them, it'll take you to the abstract and the recordings, which are on YouTube. So if you missed anything and you want to watch it again, you can go ahead and do that. Okay, and again, everyone is muted. Questions, please put into the Google document. So I'm going to pass it over to our first speaker today. Okay, we can see your entire screen, but you need to unmute yourself, please.
Okay, can you hear me now?
Yes, I can. Perfect. Thank you so much.
Okay. Thank you. Hello, everyone, and thanks for joining my talk. I'm a second-year PhD student at George Mason University, and this work, which I will be showing today, is done in collaboration with my PhD advisor, Christina Stan. So I will talk about a novel pre-processing tool based on machine learning, namely the convolutional neural network, that extracts the intraseasonal variability in the operational monitoring and forecast data. So the main motivation for why we wanted to go to the machine learning approach to extract the intraseasonal variability. It's known that intraseasonal oscillations are the dominant modes of tropical variability that modulates the precipitation in the tropics. To understand the mechanisms responsible for these oscillations, first step is to isolate these oscillations in the observational or reanalysis data. So this is done usually using the Fourier filters and weighted filters, for example, Lankos. But the problem is these techniques do not work for forecast or real-time observations. For instance, if you want to filter the intraseasonal variability in a 3-month CFS forecast using a conventional bandpass filter, let's say Lankos, it leaves with the missing data in the both ends, and we require some extrapolation to fill in those gaps. So we developed a method based on machine learning, namely convolutional neural network, to extract the intraseasonal anomalies in operational monitoring and forecast data. So first of all, before talking about the performance of the CNN filter, first I'll talk about the convolution operation, which is the core mathematical operation in the neural network. Then I'll briefly talk about how neural network works, and then I'll talk about the specific details of the CNN architecture we used in this study, and also the data we use for training and testing, and also some of the CNN model hyperparameters. So to begin with, the convolution, as seen here, for example, in the red line, let's suppose these are signal. Let's say these are OLR or precipitation or wind stress, and we want to extract in these signal, we want to extract the intraseasonal variability. So let's say we have the kernel with some weights here, and the convolution operation, which is shown in this equation, is just the sliding dot product of kernel weights with the signal. And the way the convolution operator works in the neural networks is, let's say, suppose we have daily zonal wind stress anomalies as an input here. And in the forward pass, these input time series is multiplied with some weights. And these weight and the summation of the product of these signal and the weights is then again go through some linear or nonlinear operator, and the resultant output is compared with the actual output. So for this case, we actually compare with the 32 90-day filtered zonal wind stress anomalies, which are extracted using the Lancos. And the error is back propagated in such a way that the weights are adjusted so that the loss function is minimized. So this forward and backward pass, one forward and backward pass is an epoch, and this is repeated for many number of epochs. So the architecture we'll be using for this study, let's say we have a spatial data that is we have temporally spatial data. And the first thing we do is regrid the data. So each grid point has the time series here. So there are a lot of grid points stacked with the time series. And what we do is we apply a 90-day convolution on each grid point, and the output from this convolution is subtracted from the input layer. This is the and then the output from this layer, we do again the 30-day convolution on this layer, and the resultant we again regrid those data into the spatial and temporal. So this is the main CNN framework we want to use, and this step is repeated many times in such a way that the kernels, the weights of the kernels in the 90-day, and the kernels in the weights of the kernels in the 30-day is optimized. So this is repeated at every grid point. So we have weights at each grid point. Unlike in Lancos, we have a fixed number of weights, and the fixed number of weights is applied throughout the grid point. Here we have custom weights for each grid point. So the data we'll be using for training, we'll be using two data sets. One is a blended scatterometer daily zonal wind stress anomalies. The training period we use is between 1988 to 2014, and we test the CNN model for 2 years, 2015 and 2016. Also, we use NOAA interpolated daily OLR anomalies, and we train this the CNN model using period between 1980 to 2018, and we test this CNN model for 2 years, 2019 and 20. So the optimizer we use is Adam optimizer, and the loss function we want to minimize is mean square error, and total of 500 epochs is used to tune the model. So again, the truth here is the Lancos filtered anomalies. Using these anomalies, we will train the model. So now I'll show the results. So first I'll show the performance of the CNN filter. And then I'll show two applications of CNN filter. One is a reconstruction of MJO zonal wind stress, and the other application is real-time filtering of intraseasonal anomalies. So here I've shown the hallmark of zonal wind stress anomalies. On the left side is the daily anomalies plotted for the year 2015. And the second panel is 30 to 90-day anomalies filtered using the LANCOs. And the third one is 30 to 90-day anomalies filtered using the CNN, which is trained using the data. And the last panel is the difference between the second and third. As we can see in the third plot, we can see the intra-seasonal anomalies. The CNN filter could able to preserve these anomalies and the propagation capture nicely, but there are differences associated when we look at the difference plot here. So the CNN filter does not only preserve the propagation features, but also it preserves the total power associated with the signal. So the plot shown here is the power spectral density of LANCOs filtered 32 to 90-day anomalies and CNN filtered 32 to 90-day anomalies. The blue is the CNN and the red is the LANCOs. So we can see the CNN is able to pick the peaks at 40 and 60 days. And also it able to preserve the total power in the signal. So again, we also tested with the OLR. So here I shown the hallmark for the 2019 year, and on the left is the daily anomalies, and on the second one is the 25 to 90-day anomalies filtered using the LANCOs, and the third one is the 25 to 90 days anomalies filtered using the CNN, and the last one is the difference between the 2 and 3. So CNN is able to perform very well when we compared with the LANCOs. So here LANCOs is the truth for this study, and also the difference is also is negligible. So when we compare the magnitudes, the magnitudes here, and when we compare the difference magnitude, it's minimum. And not only the CNN filter able to preserve the propagations here, but also it able to preserve the total power, as we can see from the power spectral density plot. So it almost captures the power spectrum in comparison with the LANCOs filter. So next, I did some error analysis in comparison with the LANCOs and CNN filter. So I want to introduce a metric which I used for comparison called index of agreement. So here O implies the observed, which is LANCOs in this case. The P is predicted, which in this case is the CNN. So the index of agreement, it represents the ratio of the mean square error and the potential error. So the agreement value of 1 indicates a perfect match and 0 indicates no agreement at all. So on the top, on the top is the root mean square error for the zonal wind stress and index of agreement. On the bottom, I have shown is the root mean square error and the index of agreement between the LANCOs and the CNN. So when we look at the index of agreement, the values are close. They are greater than 90 at most of the locations. And when we look at the OLR, also the RMSE is less. And also the index of agreement is more than 98 at all longitudinal points here. So, and also we tested the sensitivity of the convolution kernel size. So we used 30 to 90, and we want to test whether there is a sensitivity, whether we change the kernel length, whether the RMSE or index of agreement changes drastically. So on the top is the zonal wind stress plotted is the, on the x-axis is the kernel 1, and on the y-axis is the kernel 2. So the numbers indicates the convolution length. So when we look at the RMSC here, we don't see much changes here, even though it changes from 5 to 6. But the kernel size we used is 3290, and the RMSC is 5. Sorry. So the RMSC is close to around 5.6, and when we choose the kernel size 70 to 50, it's worst, and there is no. And when we choose 120 and 30, there is a slight improvement, but it's not that significant. So when we look at the OLR, it's the same. We selected 30 to 90 day as the kernel 1 and kernel 2 size. So for the 60 and 15, the RMSC is bad, but when we look at the magnitudes, it's not that relevant. So from this, if you change the kernel length, our results won't be much sensitive. So now I want to show the application part of it. So since we looked at the performance of the CNN filter and we are convinced that CNN could able to extract the features similar to the Lancos, we want to apply the CNN filter to see how it can be used for the reconstruction of MJO zonal wind stress. So Leiberger and Stan developed a dynamical framework for forecasting MJO influence on El Nino, but this dynamical framework requires MJO filtered wind stress as input. So this framework works very well for the reanalysis data, but when we apply to the operational monitoring or forecast data, so the MJO zonal wind stress is constructed from the unfiltered wind stress anomalies using Hilbert singular value decomposition. So when we reconstruct the MJO signals from the unfiltered wind stress anomalies, so in the unfiltered wind stress anomalies, a lot of frequencies are retained. So we can apply the CNN filter first on the time series, and then we can apply, and then we can project the dominant EOFs onto the CNN filtered anomalies. In this way, we can isolate the dominant features. We can improve isolating the dominant features. So first of all, so I'm showing here is the time longitude harmolar of index of agreement that I introduced before. So the index of agreement is between the zonal wind stress, MJO zonal wind stress constructed using the Lancos filtered anomalies, and the zonal wind stress, MJO zonal wind stress constructed using the CNN filtered anomalies. So this is the metric that tells us how well it able to represent the Lancos filtered anomalies. So when we look at this plot, at most of the locations, the index of agreement is greater than 95 for most of the years, but there are a few years, for example, in 1995, these locations, the index of agreement is close to 90, but overall, it very well matches with the Lancos filter. But the real comparison is to be done with the MJO zonal wind stress constructed using the unfiltered anomalies. So the plot here shown is a difference plot between the plot which I showed previously and the index of agreement between the MJO wind stress constructed using the Lancos and the MJO wind stress constructed using the unfiltered anomalies. So here we can see at most of the locations the MJO reconstruction construction using the CNN filtered anomalies outperforms the MJO reconstruction using the unfiltered anomalies. But at few locations and few years, it is comparable with the unfiltered anomalies. So this is one of the application where if we want to extract the MJO wind stress signals in the forecast data, So first we can apply the CNN filter on the time series data, and then we can project the dominant EOFs onto the CNN filtered anomalies to get the dominant structures. So I want to move on to the second application of the CNN filter, that is for the real-time filtering of intraseasonal anomalies. So the conventional method used for real-time extraction of intraseasonal oscillations is generally the principal components based on the daily anomalies are projected onto the dominant EOFs to reconstruct the ISO signals. I want to compare with an approach by Kikuchi 2020. He used extended EOFs to reconstruct the MJO and boreal summer intraseasonal oscillations. So before projecting onto the dominant EOFs, first he filtered the low frequency and high frequency signals by subtracting the mean of previous 40 days from the daily anomalies and then applying the 5-day tapered running mean. However, this process can be, this extraction of IOS in the recent observations can be improved by first applying the one-dimensional CNN filter on the daily anomalies and then projecting onto the dominant EOFs. So now I'll show the CNN filter method and the Kikuchi method in the next plot. So on the left-hand side, it's a hormonal of the OLR. So the values below the red line in both the plots is the Lanco's filtered 25 to 90-day anomalies in shading, and the counters are MGO reconstructed using the Lanco's filtered 25 to 90-day anomalies. So on the top is the real-time recent observational data, which Lanco's has a missing values there. So on the left-hand side shown is the shading is the anomalies calculated using following the Kikuchi, as I discussed previously, and the counters are the MJO counters reconstructed using the anomalies. And on the right is the CNN filtered 25 to 90-day anomalies in the shading, and the counters are MJO reconstructed using the 25 to 90-day CNN filtered anomalies. So as we can see, the 25, when we see the daily anomalies in the shading, it's more smooth when we apply the CNN filter, but on the left-hand side, there are other frequencies as well, which are other than in 25 to 90 in the signal. And also the transition is smooth here when we go from go below the red line and to the above red line, we see a clear smooth transition. So to conclude, we have seen that CNN filter could able to preserve the propagation features and the total power of the intraseasonal anomalies. So we also looked at the MJO zonal wind stress constructed using the CNN filtered anomalies has a greater index of agreement score than MJO zonal wind stress constructed using the unfiltered anomalies. So this approach can be used for on the forecast data as well to isolate the MJO signals. So we also seen the real-time extraction of intraseasonal anomalies can be improved using the CNN filter. And the main takeaway is the CNN filter can be applied to operational monitoring and forecast data for extracting intraseasonal variability. So the CNN filter is flexible as well. So if you want to extract the 2 to 20-day variability in the data, we can tune the model in such a way that it extracts the 22 to 20-day variability. But one limitation is of this CNN filter is we have to have a minimum number of days, which is equal to the frequency, the higher, the larger time period we used. For example, if you want to extract 30 to 90 days, the minimum length of the data should be at least 90 days. And with this, I want to conclude and happy to take any questions.
Great, thank you so much. If anyone has any questions, please type them into the discussion document. I've put the link in the chat.
Karen, how can I get the access for the
Oh,
Google document?
let me just share the screen. That'd probably be the easiest, so everyone can see. Okay, here we are. Zoom in a little bit. All right, can you see the screen?
Yeah, I can see the screen.
Okay. Looks like we have a question. If you could go ahead and address this one.
So Lankos is a weighted filter. So to extract the signals in a particular bandwidth. So Lankos filter is a traditional filter used in the data analysis. So we consider the Lankos filter as Lankos filter anomalies as a truth, and we want to test how the CNN performs in comparison with that.
Okay, we'll give it one more minute to see if there's any more questions. If not, we'll pass it to our second presenter. Here's a question: how does CNN extract the subseasonal information in real time?
Yeah, so first we will train the CNN model using the past data. So once we obtain the weights of the convolution operator, and then it's just a simple Python implementation. Yeah, and also CNN does not require any future data. It relies on the present data.
Okay, one more question's coming in, and this will be our last one. But if anyone has any additional questions, you can go ahead and keep typing. Is it overly simplistic to consider the CNN as a kind of spectral filter for the data? And if I've misinterpreted, can you explain what the convolutions achieve?
So the convolution operation mathematically is a dot product between the weight. So dot product between the weight of the kernel and the time series data. So the weights of the kernel is a way it can isolate the it gives the weight for the data. So it assigns weights for each value in the time series in such a way that it retains only the variability between the a particular bandwidth we use. For example, in this case, we used 30 to 90 day.
All right, thank you. We need to move on to our second presentation. But again, if you have more questions, go ahead and type more on here. And the speakers can answer after the time as well.
Thank you.
Okay, thank you very much. I'm going to pass it over to Edmund now. All right, I can see your full screen.
Okay, great. Can you hear me?
And I can hear you.
Okay, great. Thank you. Yeah, thanks everyone for attending. Today I'm going to talk about developing and verifying a subseasonal outlook tool for extratropical storminess. This is a collaborative project between Stony Brook University and NSF CPC. Our CPC collaborators are Wenqiu Wang and Yutong Pan. This talk will be separated into two parts. In the first part, I will discuss some background information, including describing the storminess indices, as well as some hindcast assessments. Then Yutong Pan of CPC will take over and describe the preliminary version of the near real-time outlook tool that CPC is setting up. Extratropical cyclones can give rise to high impact and extreme weather, including heavy precipitation, high winds, and coastal storm surge. Thus, it is important to provide outlooks to stakeholders to warn them of potential upcoming hazards. Now, individual cyclones can be predicted out to about a week. From week 2 and beyond, prediction of storm statistics or storminess is more useful. There are two kinds of definitions for storminess. We can track the cyclones and provide information about cyclone track, frequency, and amplitude. Alternatively, passages of cyclones give rise to pressure changes, and hence quantifying the synoptic timescale variance in pressure can provide an alternative measure of storminess. Our previous studies have shown that both track statistics and variance statistics are highly correlated with significant weather. Here I will show you some examples of these storminess indices. Given the cyclone tracks, we can calculate how many cyclones pass within a certain radius in any grid box, and this is called track frequency or track density. Here, for winter, we can see that the highest frequencies over the Pacific, across North America, and the Atlantic into Europe. We can also compute the average amplitude or intensity of the cyclones. We can see that in winter, the deepest cyclones occur near the Aleutian and Icelandic low regions. Previous studies have shown that cyclone tracking is most uncertain for weak cyclones and most robust for stronger cyclones. Hence, we mainly focus on cyclones that are deeper than 1,000 HPA. Here, sorry. I will also show some results on how models do in predicting deep cyclones that are deeper than 907 HPA. These cyclones mainly occur in winter near the Aleutian and Icelandic low regions. Over regions where cyclones frequently track through, pressure will change rapidly when these cyclones move across the region. Hence, the magnitude of variance of pressure changes at each grid box provides an alternative measure of storminess. This panel shows the winter distribution of this sea level pressure variance storminess metric, which is again largest over the Pacific and Atlantic storm track regions. Comparing this sea level pressure variance metric to this track frequency, we can see a lot of similarities. Although the pressure variance metric is affected not only by cyclone frequency, but also by the intensity. For hindcast assessment, we make use of model hindcast data to assess how models do in predicting the storminess indices. We examined GAPS 12, 35-day reforecast, which are initialized once every week with an 11-member ensemble, and CFS-V2 reforecast that are initialized once every 6 hours, but with only 1 member. Hence, to form a CFS-V2 ensemble, we used a lagged ensemble strategy with 12 members, meaning that we use hindcasts that are up to nearly 3 days old. For verification, we compute the anomaly correlation coefficient, or ACC, between reforecast predicted storminess anomalies and observed storminess anomalies derived from reanalysis data. We examined both week 2 and weeks 3 to 4 hindcasts. Since this talk focuses on weeks 3 to 4, I will only show one slide for week 2. The top row shows hindcast ACC for threat frequency, while the bottom row for threat amplitude or intensity. The left column shows results from GAPS 12, the middle column for CFS-V2, and the right column shows results from the combined GAPS 12 CFS-V2 ensemble. We can see that both models show good ability to predict both threat frequency and amplitude over the main storm threat regions for week 2, with GAPS 12 showing slightly higher ACC scores than CFS-V2, which is not surprising since the CFS ensemble is a lagged ensemble, including forecasts that are up to 3 days old. Nevertheless, the combined ensemble does better than either individual ensemble. This is true for all cases that we have examined, and hence from now on, I will only show results for the combined ensemble. For weeks 3 to 4, ACC scores are much lower than those for week 2. Even the combined ensemble shows rather low ACC scores for either threat frequency or amplitude, except over isolated regions. The ACC for the frequency of moderate cyclones, those with central pressure lower than 1000 HPA, is slightly higher. The ensemble shows some ability to predict this over the Eastern Pacific, as well as off the east coast of North America and over parts of Eastern North America. On the other hand, the ensemble shows very little ability for predicting the frequency of deep cyclones with pressure lower than 970 HPA for weeks 3 to 4, although they show quite good ability predicting this for week 2. Among track statistics, the models predict the accumulated track activity, or ATA, best. The ATA is a novel measure that we developed that combines information from track frequency and amplitude. Models show some ability in predicting this metric over the Eastern Pacific near Alaska, as well as off the east coast of North America, extending into the Atlantic in winter. The model shows the highest ACC scores for predicting the sea level pressure variance storminess metric. This metric integrates information from both cyclone frequency and amplitude, and is generally much smoother than any of the track statistics considered, potentially making it more easy to predict than cyclone track statistics. Models show some ability to predict this metric over the parts of Eastern Pacific, near Alaska, over parts of North America, over the Atlantic, and over Eastern Asia. So far, I've only shown results for winter. This figure shows the ACC scores for the prediction of sea level pressure variance storminess metric for the different seasons. Each panel represents results for from 2 months. Models do best in predicting storminess in the cold months, December and January on the upper left, and February and March in the upper central panel. In spring and fall, which are shown in the right-hand side, models show some ability to predict storminess over the Pacific, as well as over parts of Eastern North America. The ACC scores for summer months are very low, except in some isolated spots. So in summary, our results show that the combined GAPS 12 CFSV2 and sample consistently does better than either individual and sample. In week 2, the models show good ability for predicting both cyclone track frequency and amplitude. For weeks 3 to 4, ACC scores for track statistics are generally rather low, except for the accumulated track activity of the Eastern Pacific and just off the US East Coast. The ACC scores for the sea level pressure variance statistics are generally much higher than those for the track statistics. Given these results, we decided to include both track statistics and variance statistics in our outlook. Track statistics are more familiar to forecasters and include more information such as number of cyclones and cyclone intensity, but they are not well predicted by the models at weeks 3 to 4. On the other hand, the sea level pressure variance statistics is better predicted by the models, but it is not as familiar to forecasters. It contains less information since it integrates information from both track frequency and amplitude. Hence, we recommend users to make use of both types of Storminess indices. So I'll now hand over to Yutong Pan, who will describe the near real-time outlook tool that is being developed at CPC.
Okay, good afternoon. I'm Yutong Pan from NOAA CPC. I'm going to talk about the real-time forecast products of subseasonal storm track over North Pacific, North America, and the North Atlantic. The project goal are to develop week 2 and week 3-4 storm track forecast tools to verify the forecast and evaluate the forecast skill. Next slide, please. Okay, the outlooks are based on dynamic forecast from 2 models. GAPS 12 16-day data for week 2 forecast, 35-day for week 3-4, and CFS2 45-day for week 2 and week 3-4. For model climatology and forecast skill assessment, we used GAPS 21-year hindcast, CFS2 12-year hindcast. Now this 12-year has been extended to 21 years. Currently, we are working on using CFS2 21-year hindcast to update our storminess outlook and scale evaluation. For observation, CFSR data are used for forecast verification and the scale assessment. Next slide, please. Okay. Storm detecting and tracking are based on the algorithm developed by Dr. Series using these listed criteria. We also derive storm track density, storm intensity, and storm duration using a domain of 250 kilometer radius for storm statistics at each grid point. Because 1,500 kilometer is often used in the climate community, so later it would be worth testing 500 kilometer radius to accumulate storm statistics. Next slide, please. Product, here list all the variables in the outlook products, including storm activity, precipitation, 10-meter wind, sea level pressure, and sea level pressure day-to-day variance. The outlook consists of both deterministic forecast and the probability forecast. Next slide, please. Okay. The forecast products and the verification are available at this real-time forecast website with a daily update. This is a web page layout for forecast date January 30, 2021. You can find week 2 and week 3-4 forecasts for GAPS in the up table, CFS in the middle, and GAPS CFS combined forecast in the bottom over North Hemisphere. The website also provides regional maps over Alaska Arctic, North Pacific, North Atlantic, and North America. Yeah, next, please. This is an example of GAPS week 3-4 forecast, showing the storm activity. Left panel total field, and the right side anomaly. You see larger spread in the storm tracks, indicating relatively large uncertainty in the stormless forecast at week 3-4 time range. In the track density field, you can see storm activity in both North Pacific and North Atlantic. Next, please. Okay, forecast of CFS2 is similar to GAPS. Next, please. This is a forecast. Combine GAPS and the CFS. Basically, it is an ensemble average of all members from the two models. Yeah. Next slide, please. CFSR verification of model forecast. Here shows the verification of GAPS week 3-4 forecast. One panel for total field and one for anomaly. Left side in each panel is the GAPS forecast showing in the previous slide. Right side, the verification. The week 3-4 forecast is consistent with observation to some extent. Yeah, I'm just showing some forecast example. Again, you can find all the products and the verification at the forecast website. Next slide, please. This is an assessment of GAPS week 3-4 forecast. Anomaly correlation of storm track density for January and July. Dashed line circled area are climatologically storm active region from CFSR. We see a relatively high scale in the storm active region, and winter months has higher scale than summer months. A result for CFS and the combined forecasts are not shown, but they have a similar distribution and scale. Next, please. Anomaly correlation of sea level pressure day-to-day variance for GAPS week 3-4. Sea level pressure variance is also a measure of storm activity. It has a better scale than track density. Scales for precipitation and sea level pressure are also higher than track density, which are not showing here. Okay, next one, please. Okay, a summary for the real-time outlook tool. We have developed subseasonal stormless outlooks. Assessment of forecast indicate a certain level of scale in track density at extratropics. Precipitation, sea level pressure, and its variance have better forecast scales. Scale in operational forecast are expected to be higher because of a larger operational ensemble than hindcast. Next, we will test increase in ensemble member by using up to 3-day lag to improve the forecast. Yeah. Okay, I will stop here. Thank you for your attention. Okay, if you have any question, please feel free.
Yes, thank you. I will show the discussion document again. So if you have any questions, please type.
Okay, let me pick up these questions. So what are the sources of predictability for weeks 3 to 4 storm track activity? Our previous study actually have shown that there are several potential sources of predictability, including tropical heating, ENSO and MJO are some of the potential sources, and then also stratospheric anomalies like large-scale teleconnections, such as the polar vortex variability, as well as actually the QBO actually also affect storm track. Our assessment suggests that actually the models get much of the influence, seems to be able to forecast quite a bit of the influence of ENSO, as well as the polar vortex variability, but struggles to predict well the impact of the MJO and the QBO. So that's what we're seeing. So we're actually right now looking at potentially other tropical heatings apart from the MJO to see whether we can find additional sources of predictability. This is a good question. I'm not an expert on this, but it seems that some of the polar vortex events are predictable prior to its occurrence, while some are not. Nevertheless, it seems that the influence of the polar vortex actually lasts for a few weeks. And so even if the occurrence of the polar vortex variability, basically the sudden warming, is not predicted out to 2 or 3 weeks ahead, even if it's only predicted a few days ahead, but the influence of that actually lasts a few weeks. And so there would be some, if the model can get that even a few days ahead, they can actually have impact on the week 3 to 4 forecast. Yeah, that's a great question, and I think that's something that we're still working on. But I showed the figure in which, in the prediction hindcast results, and what we found is that the prediction, the models actually do best in predictions in the winter months, and not as good in the transition seasons, and did most poorly in summer. So that's, and most of the sources that I've mentioned are most active in the cold season, and so that may be the reason. But that's actually something that we are still working on. That's a great question. We haven't looked at the seasonal dependence of this yet.
Okay, looks like all the questions that we have for now. Again, I'd like to thank all three of our presenters today for giving talks. And thank you everyone for attending today. Our next webinar will be on April 4th. Thank you everyone.
Thank you.
Thank you. Bye-bye.
Bye.